asking if the 0 is in V, I guess.
If there's a 0 in V, that maps to Z.
Yeah, there's a 0 in V because V is a vector space. There's a unique one. So we want to know, is that one in T inverse of Z? But maybe we don't even know what T inverse of Z means. If not, we're definitely stuck. So let's figure that out first. What does it mean to take a set over on the right-hand side of this picture and pull it back under this function? If I give you a thing, how do you check if it's in there? Yes?
T applies to that thing when V and Z.
That's right. The T inverse of Z is the set of all the stuff that when you T it, it takes you into Z. Right? If you apply T and it takes you somewhere that's not in Z, then you're not in T inverse of Z. And if it takes you somewhere that is in Z, then you are in T inverse of Z. Right? It's just a concept of a pre-image. No linear algebra, just plain function stuff. This, just by definition, means precisely that T of the 0 vector in V is indeed in this set Z. So that's what we have to check. And why is it the case that T of the 0 vector in V is in capital Z? Yes?
0 vector, which maps to the 0 vector.
That's right. The 0 vector always maps to the 0 vector. We proved that from just the definition of linearity. You just plug C equals 0 in, and it gives it to you. So that means that we're really checking whether the 0 vector in W is in Z. And why is that necessarily the case? Yes?
It has to be because C is a subspace of W, and that's one of the requirements for a subspace. That in order for Z to be a subspace of W, it has to contain W's 0 vector.
Great. All right, so nothing really, hopefully nothing caught us by surprise there. Maybe you get stuck because you forget what a preimage is, or you forget what you need to check for something to be a subspace or whatever, but nothing too tricky. So that's the first bullet point. And then we also need to check closure under addition. So if you have two vectors that are in T inverse of Z, is it necessarily the case that V plus W is in T inverse of Z? Right, so once again, if we're proving an if-then type statement, we assume the if part and try to work around to get the then part. So we're over here, we've got V and W in T inverse of Z, and we want to say what that means so we can try to do something with it, get somewhere with it. So what does it mean? Yes?
It means that TV and TW are in Z.
Great. It means that TV and TW are in Z. So TV is in Z, and TW is in Z. All right, and here we have to think just a little bit. So there's some slight pushback the problem gives us. It's right here. What do we need to do next? Yes?
Is TU plus TW.
Yeah, maybe we feel stuck here actually. So let's try to work backwards to see what this thing that we're trying to conclude means. V plus W being in T inverse of Z, this thing would say that T of V plus W is in Z. So given that T of V is in Z and T of W is in Z, how could we ensure that T of V plus W is in Z? Yes.
Probably some linearity.
Apply linearity. So this last thing that we're trying to show is true if and only if t of z plus t of w is in z.
And by property of the subspace, it has to be closed in vectorization.
And there's a third thing to check, which is that it's closed under scalar multiplication, and it really is the same as this. I'm actually just going to leave it off completely. Yes?
I mean, can't you just say that it's got multiplication as TV plus TV or something like that? And that shows that that's got multiplication is closed under that.
Well, there shouldn't be a plus in there. Once we switch to looking at scalar multiplication, it's just going to be a matter of pulling the scalar out instead of...
I'm saying that TV plus TV would be 2 TV or something like that.
Right. But that only works... Yeah, so scalar multiplication is compatible with vector addition when you have an integer. Like 3 times a vector is always that vector plus itself 3 times. But that only tells you about integer scalar values, and you want all real scalar values. So you end up needing to do it separately anyway. Yes.
Is that W in part 2 the same as the W above?
No, that it's supposed to be a little w, and this is a capital W. Capital V. Yes.
You talked a little bit about computing inverses and determinants by hand. And in particular, do we have to do big ones? Like, will we regret relying on liberal source?
No, I don't want to disincentivize you to use technology. You do need to know the algorithm. So, for example, I gave you on the practice midterm, I gave you a question where it was a long, nasty calculation problem that had been fully solved for you up until the very last step. So you had to do one step and then know what you were looking at, and that was it. That's kind of the flavor of how I want to do computational problems. I'll do the computational heavy lifting, and I'll count on you being able to figure out what you're looking at. So you can still get in trouble if you don't know what you're doing, but you should not have a sore hand at the end of this. Yes?
It's a problem on 6.
Okay. Okay. All right, this was a homework problem. Show that if A is a 3 by 5 matrix, then the determinant of A transpose is 0. Yes,
Do A transpose and then A, does that matter?
it matters. It definitely matters. But was A 5 by 3 or 3 by 5? Is it? Did I get it wrong?
That is with common sense.
I feel like it should be this way, but it must have been right. Someone would have corrected it. Oh, right. I fell into the trap of confusing which way function composition goes. I want to apply A first, and then A transpose, and that makes it look like this. Okay. Well, actually, I mean, from our current vantage point, we understand how this works better. The fact that this matrix A transpose A can be written as a 5 by 3 times a 3 by 5 means what about its rank? Right. It means that its rank is no greater than 3. So that means its rank can't be 5, so it can't be bijective, so its determinant is 0. But that's cheating because it was on homework 6, and we didn't learn that until last week, so we shouldn't do it that way. Let's just talk about A. What's the nullity of A? Just based on its dimension as a 3 by 5 matrix. Or what can we say about the nullity? It's at least 2. It's mapping a 5-dimensional space to a 3-dimensional space. So just by virtue of pivot counts, or however you want to think about it, you can think of it in terms of bases if you want. Sending 5 basis vectors to 3, it's going to have to sort of squeeze 2 out. Whatever. Think about it in terms of pivot counts if you prefer. These are matrices, so it's fine. So that means that there's a whole 2-dimensional space worth of vectors that A already maps to 0. So what does that tell you about A transpose A? What's A transpose A going to do to all those vectors? So I'll give you a bunch of vectors, a 2D space's worth of vectors, and I'll tell you A maps all of these to the 0 vector. What's A transpose A going to do to all those vectors? Yes.
It has to put them to 0.
Yeah, it has to map them to 0. The null space of A transpose A contains the whole null space of A. Because if AV is 0, then A transpose A times V is going to be A transpose times 0, since we already know AV is 0 right there. And then any matrix times 0 is 0. So A transpose A might have more stuff in the nullity, but it has at least as much stuff. Sorry, in the null space. But it has at least as much stuff, so it definitely has at least a 2D space worth of vectors that all get mapped to the 0 vector. And what does that mean about A transpose A vis-a-vis its determinant? Yes.
0.
Yeah, the determinant is 0, because what would the nullity be for a matrix whose determinant is non-zero?
0.
It would be 0, that's right. All right, if it maps a whole lot of vectors to the same vector, then it's not injective. So it's not bijective. So if you want to think about this graphically with smaller numbers, if you have a map from R3 to R2, and then you compose that with a map from R2 back to R3, then all of space here is just going to get mapped down to this plane, or maybe something even smaller. And then this map from R2 to R3, best it can do is stick a plane somewhere in space. Map all those points on the plane to some plane in 3D space. There's no way for it to fill out 3D space again once you've smashed out a whole dimension. Yes?
Can you explain, and tell me if I misheard this, but you said the nullity of a matrix whose determinant is non-zero must be zero. Can you clarify that?
Right. If a matrix is going to have non-zero determinant, that means it's going to be bijective. Right? We learned that a matrix is bijective if and only if its determinant is non-zero. And if it's bijective, the only thing that maps to zero is the zero vector. And definitely the zero vector does. If it's bijective, nothing else does. That means that only the zero vector gets mapped to zero. So the null space is just the set containing one vector, the zero vector. And the dimension of the zero subspace, the subspace containing only the zero vector, is zero. So the nullity is zero. Yes?
Could you go over an example that requires the use of Cramer's rule?
Okay. So remember, Cramer's rule tells you that to solve some equation ax equals b, where A is a square matrix and B is some vector, you can find the ith coordinate of the solution by taking the determinant of the matrix you get when you take the columns of A and replace the ith one with B. And then just divide that by the determinant of A. So that's Cramer's rule. Where A1 up to AN here are the columns of A. So you take the coefficient matrix, pull out the ith column, and replace it with the stuff on the right-hand side. Work out that quotient of determinants, determinant of new matrix divided by determinant of old matrix, and that's the ith component of your solution. So that's Cramer's rule. And what happens when it tells you that xi is 0? What would that mean? By the way, this A, this is an invertible matrix. All right, it needs to be, otherwise we can't be dividing by its determinant. So if xi in this formula is 0, what does that tell you is equal to 0?
Numerator.
That numerator is to 0. It has a determinant of 0. And why does that make sense? How could we have arrived at that conclusion by other means? Yes?
B is a linear combination of the vectors that are in A, like B is in the span of A.
That's right. If the determinant of this square matrix is 0, then that means that the columns are linearly dependent. Because if all the columns were linearly independent, then the matrix would be invertible, and the determinant would be non-zero. So if the determinant is 0, there's some linear dependence relation among the columns, and that linear dependence relation has to involve B, because we all already know that all the A's are linearly independent. Right? So in other words, B is in the span of the other columns, all the A's that don't involve A sub I. All the A's besides A sub I. So given that information, if I ask you how many AI's do you need to come up with B, what's the answer? To come up with B as a linear combination of all the A's, including AI, how many AI's do you need? Right. It's very quiet, but you need 0. And in fact, that's exactly the question that the original equation asks. Whenever you see this equation, AX equals B, what that's saying is, what are the weights that you need to combine the columns of A so as to get B? That's just because that's how we define the matrix vector product. A times X is the linear combination of the columns of A with weights given by the components of X. So Cramer's rule tells us we need 0 AI's to come up with B as the linear combination of the columns of A. And we worked out that same conclusion through this other more, well, through some means that didn't involve invoking Cramer's rule. Yes?
So, like, that's pretty, you could just know that through intuition, like, just by looking at the equation A is equal to B, knowing that xi equals 0. Like, you could,
Yeah, yes, right. Yeah, that's in a sense, that's the point of this question.
yeah.
It's like a sanity check on Cramer's rule. Like if you misremembered Cramer's rule, you could think of something like this and hopefully it would break and you'd be like, oh yeah, I messed up Cramer's rule. But we didn't. That's the right one. Yes?
Can you check much of intuition for why one
Yeah, because the determinant tells you, and I can't stress this enough, it's my opinion that the absolute most important thing about a determinant is that it's a factor by which signed volumes are transformed. So if you don't know that, you should know it. It's very important. It's sort of the only thing that matters about determinants at the end of the day. How long was that up? That's embarrassing. I've got to figure out how to, well, whatever. I can handle being embarrassed. The thing is, I don't know what she said, other than she's at rehearsal or something like that. Okay, so if you have two vectors that are not, okay, now I can know what she said. Is 10 an optimistic or realistic arrival time? So suppose we have two vectors that are orthogonal to each other. They're at 90-degree angles. And we see where they go. So those are going to be the columns of our matrix A. And we determine that they end up going to two vectors which are very nearly pointing in the same direction. And actually, I'm going to need to scale this down because I'm going to run out of space when I try to make the parallelogram. So originally they spanned this parallelogram, just this square, and then now they span this really little one. At least turn the sound off. I think you can also, yeah, okay.
You gotta make your iPad do not disturb.
Yeah, you're right. You're right, but awesome. I'm glad you knew. All right. So if we have a linear transformation that takes two vectors that trace out the unit square and maps them to two vectors which are very nearly parallel, what can you say about the determinant of A? It's very small because it mapped a unit area thing to a very small area thing. And conversely, if I tell you the determinant of A is really small, that means that maps E1 and E2 to vectors which are close to each other. Or maybe they're not, but they're just really short. But either way. So the determinant of A is small if and only if all right, and typically you can just look at them and tell they're not really short, so that means they have to be close to parallel. The vectors E1 and E2 are mapped, yes, the vectors that E1 and E2 are mapped to, which is to say the column vectors of the matrix, are nearly parallel and or really short. I'm assuming you're squinting because you have a hard time reading it.
Yeah.
Yes.
What do we
So I think that the question was, what do we need to know about rook arrangements? Nothing expressly. I won't ask you about rook arrangements because I'm not sure that the students in the other sections focus on that. But you might need to know, so for example, I don't remember what the numbers are. I'm just going to make up numbers. So there was a question that was very much of this flavor on the practice midterm, and it requires you to do not necessarily rook arrangements per se, but something in that family to really get it right. So the question is, what are the values of x that make this determinant equal to 0? And you should very quickly recognize what the answer is, but showing that that's actually all the answers requires a little more thinking. So right off the bat, just what does x need to be here?
Not plus or minus.
Yes, except without the not.
Wait, was it return?
We're trying to make this determinant be 0.
No, then yeah, plus or minus.
So plus or minus 2, because that makes the first and third rows equal, and then we're one row operation away from having a row of all zeros. So the matrix is definitely not bijective, so its determinant's going to be 0. So right away we have that x equals 2 and minus 2 work here. But how do we know there aren't other values of x that work as well? Yes.
You said that you went to the identity matrix and then solve it out.
Yeah, maybe. That's too much work, though. So let's say you were very industrious and you just worked out this determinant to just a simple expression that doesn't involve determinants or matrices. You just did everything out. What would you be looking at? What kind of an object would you be looking at? Yes.
You have a quadratic polynomial.
Exactly. You'd have a polynomial in x because everything there is either a number or power of x, and you'd be combining all those entries in a way that involves multiplying them together and adding up the results. So all of that stuff preserves polynomialhood. So everything there's a polynomial, so it would be a polynomial at the end of the day. Now, why would the polynomial that you get necessarily be at most quadratic? How do you know that's not going to turn into a cubic on you? Yes?
Everything except the x squared is like a constant, so multiply by a constant, add a constant. That doesn't make it cubic.
That's right, but how do you know x squared doesn't get multiplied by itself at some point?
Because determinants like the formula excludes anything in your row or column, so it excludes itself.
All right, so a rook arrangement, as we defined it in my class, is something like that. It's a selection of, so if it's an n by n matrix, a rook arrangement is a selection of n entries in such a way that no two are in the same row or column. So that's going to be one of the terms. It's going to involve 6 times 7 times 3 times x squared. And the full determinant is going to have one of these terms for every possible rook arrangement. And there's an extra plus minus that gets thrown in there. But that doesn't affect the role of x squared here. Some of the rook arrangements will not include x squared, and they'll just be constants. Other ones will include x squared, and they'll be quadratic. Yes? Left-hand side. Yeah, I didn't want to write those 16 numbers again. Yes?
Can you explain what a rook expansion is?
Yeah, so the determinant is equal to a sum over all the possible rook arrangements of just the product of the terms that are in that rook arrangement. So this is one rook arrangement that I've highlighted here, 763 x squared. And that counts as a rook arrangement because none of those entries are in the same row or column as each other. Like each row is represented once, each column is represented once. So the determinant is going to be equal to the sum of that term, 763 x squared, the product of those 4 things, plus another term for each other rook expansion. So there are going to be 24 in total here. So there's going to be an orange term as well as a green term. All right, so it's going to be 7 times 6 times 3 times 4 showing up in there, and so on. There are 24 total terms. And then there's also a plus or minus 1. 12 of them get an extra minus sign, and 12 of them get a plus sign. But don't worry too much about the plus minus thing. It's not that important. So like, to do a small example, the determinant of A, B, C, D, E, F, G, H, I is going to be A, E, I for the diagonal rook arrangement plus plus B, F, G. I think that one's plus because you do 2 swaps, right?
We'll just move G to the back, right? That's going to be a swap.
Well, a swap just lets you switch 2 things, right? You want to move 3 at once. Okay, plus plus BDI. Wait, no, that one's minus. All right, plus some more stuff. CDH. Whatever, this is hard. I don't think I'm illustrating anything that great. But anyway, you get the point. You just go through all the rook arrangements. Each one gives you a product of the entries in that position. And then there's a plus or a minus that goes with that term that you don't need to worry about.
Can we just like determine
Yeah, you could do that instead. The reason that I prefer the rook arrangement thing is that there's certain properties that are just kind of obvious with the rook arrangement. Like for example, if you have an upper triangular matrix, and this would be more relevant with a much bigger one, it's really clear that the only rook arrangement that doesn't give you 0 is the one that goes straight down the diagonal. 3 times 2 times 1. That's a term that goes into the rook expansion. And any other rook arrangement is going to have to dip into that lower left pool of zeros at some point and wipe out that whole term. So that tells you that the determinant of this matrix is 6. And can you do that with cofactor expansions? Yes, but it's an inductive argument, right? You say, okay, let's do it on the first column. That's only going to give me one non-zero summand, and all the rest are going to be 0. And then let's do it again and again, right? It's sort of, I mean, it's fine, I guess, but with the rook stuff, it's completely obvious. You just look at it, you're like, the only way I can put rooks on this thing and miss zeros is straight down the diagonal, and you're done. And also in the context of this question that we just did, the fact that you never get something higher than x squared. I mean, again, you can do that with cofactor expansions if you want to, but you have to do more thinking, right? The fact that x squared only shows up once in each term is a property of the definition of a rook arrangement, not something that comes from all that dealing with crossing out rows and columns and doing minors and stuff like that. But anyway, you can do whichever one you're comfortable with. It's just a different way of thinking about the same thing. Yes?
Sorry, so what were we using that root expansion to like say about the determinant again?
That it's non-zero whenever, well, the most direct thing we're saying is that that determinant on the left-hand side is a quadratic polynomial, meaning that if you did all the work to work out exactly what it is, at the end of the day, you'd be looking at something that's a quadratic polynomial. So it's equal to 0 in only 2 places, which means that we don't have to worry about there being other x values that would also work, because we know from the fundamental theorem of algebra that there are at most 2 solutions to a quadratic polynomial. Yes?
So I was doing my math lab practice stuff, and in chapter 3.3, there was something that's like adjunct or adjunct, something like that.
We skipped that.
Okay.
Yeah. The question was about adjoints, which we didn't do. Yes?
Will there be review in class on Tuesday?
What?
Will there be review time in class on Tuesday?
Yeah, there will be some review time in class on Tuesday. Yes?
Would you say why it would be useful to use like the fact that something is an isomorphism to solve the problems?
I would say don't solve any problems that way. That's
What was the word?
by using an isomorphism. I mean, that's sort of it's technically correct, but it short circuits exercises in ways that are not helpful. Like if I ask you to solve something about polynomials, and you say, forget polynomials, they're really just copies of Rn that are images of some isomorphism, and then I'm just going to work in Rn. That's what we're trying to move past.